Right now, as you sit reading this, you are moving. Not gently. You are being carried around the centre of the galaxy at more than 800,000 kilometers an hour, and you feel nothing at all because everything around you is falling at the same impossible speed. The night sky looks perfectly still. It looks, more than anything, safe, and that stillness is the most convincing illusion you will ever be shown. Because the calm band of light overhead is not a peaceful place that happens to hold us. It is a turning machine of a few 100 billion stars, anchored by a black hole, blowing bubbles with the deaths of stars, and quietly tearing smaller galaxies apart. The only reason it looks gentle is that we're watching it from the single safest, quietest lane it contains. Step out of that lane in any direction, and the galaxy stops being gentle very fast. Tonight, we're going to travel outward through it, layer by layer, and find out exactly why our galaxy gets scarier the further you go. Get comfortable. If you enjoy having your sense of home quietly turned inside out, a slow like and subscribe helps this channel reach more curious minds like you. Because by the end of tonight, that soft, familiar band of light will look less like a peaceful sky and more like what it truly is. Now, let's slowly settle into the dark. Tonight, if the sky's clear and you're far enough from city light, you can walk outside and look up at the one structure large enough to hold everything you have ever known. The Milky Way is that faint river of light spilling across the dark, and it looks like the most peaceful thing in the world. It does not move, it does not threaten. It hangs there, soft and silver and still, the way it has hung over every human being who ever lived. And the feeling it gives most of us is calm. That calm is the reason we're here tonight, because that calm is a lie, not a malicious one, just a lie of distance and timing, the kind the universe tells without meaning to, and the moment you begin to travel out into the thing you're looking at, the calm starts to come apart. Here is the question I want you to hold on to for the next 2 hours, because everything we do tonight is an attempt to answer it. Why should our galaxy get scarier the further you travel? It is a strange thing to even ask. A place is a place. The band of light overhead does not look more dangerous in one part than another, and yet the deeper you go into it, in almost every direction, the worse it gets, and the worse it gets in ways that are specific and measurable and real. By the end of tonight, you will understand exactly why the safe, gentle sky you're standing under is the single most misleading view of the galaxy you could possibly have. Let me start by telling you where you are, because you almost certainly picture it wrong. You live on a small rocky planet orbiting an ordinary star, and that star is not sitting still at the centre of anything. It is falling, endlessly, around the centre of the galaxy at a speed that is difficult to make feel real. The sun is moving at roughly 230 kilometers every second. That is more than 800,000 kilometers an hour. In the time it takes you to read this sentence aloud, you and your entire planet have travelled a few thousand kilometers around the galaxy, and you felt nothing because everything around you is falling at the same speed. The whole quiet lane you live in is moving together, and that shared motion is part of why it feels so still. The sun sits about 26,000 light-years from the centre of the galaxy. A light-year is the distance light travels in a year, and light is the fastest thing there is, crossing 300,000 kilometers every second. So when I tell you that you are 26,000 light-years from the centre, I am telling you that a beam of light, moving at the absolute speed limit of the universe, would need 26,000 years just to reach the middle of the structure you are part of. And the middle is not the edge. The galaxy is something like 100,000 to 120,000 light-years across. You're living out in the suburbs of it, on a quiet street, in a small house, and tonight we're going to leave that house and walk the length of the galaxy. And I want you to notice how the feeling changes with every step. Consider how long the sun has been making this journey. It takes the sun somewhere between 225 and 250 million years to complete a single orbit around the galactic centre. Astronomers call that span a galactic year. The sun has been alive for about 4.5 billion years, which means that in its entire existence, it has completed only around 20 of these enormous laps. 20. The last time the sun was in the position it occupies tonight, the dinosaurs had not yet appeared on Earth. An entire age of life, from the first dinosaurs through their extinction and the long rise of mammals and the arrival of us has unfolded in the time it took our star to travel 3/4 of the way around one loop. That is the clock we are living inside, and it is so slow and so steady that we mistake it for stillness, and the galaxy itself is not sitting still while the sun circles inside it. The whole Milky Way is moving through space, drifting through the larger structure of galaxies around it at hundreds of kilometers every second. Measured against the faint background glow left over from the birth of the universe, the ancient reference frame against which all cosmic motion can be judged, our galaxy is travelling at something like 630 kilometers per second, carried along by the gravity of even larger structures far beyond it. So nothing about your position is fixed. You are spinning on a planet, which is orbiting a star, which is falling around the centre of a galaxy at 800,000 kilometers an hour, and that whole galaxy is itself racing through the universe faster still. The stillness of the night sky is the deepest illusion there is. You have never once been at rest, not for a single second of your life, and neither has anything you have ever touched. There is one more number I want to leave with you before we go, because it sets the scale of what we are about to walk through. The galaxy holds somewhere between 100 billion and 400 billion stars. We do not even know the number precisely, which should tell you something on its own, that we cannot count the suns in our own galaxy any more exactly than that, because most of them are too faint and too far and too hidden behind dust to see. Every one of those hundreds of billions of stars is a sun, many of them with their own planets, their own frozen outer clouds, their own quiet or violent neighborhoods, and the sun, the star that means everything to us, the source of every sunrise and every harvest and every warm afternoon in the whole of human history, is one of them. Not a special one, not a central one ordinary star among hundreds of billions, riding a quiet orbit through the outskirts, and we are about to find out what surrounds it. Now here is the first crack, the first hint that the calm is hiding something. The reason the sky looks so gentle is not that the galaxy is gentle, it is that we happen to live in one of the calmest possible addresses inside it, and we see everything from that one sheltered spot. Imagine you were born in the single quietest room of an enormous building, a building that is, in most of its other rooms, on fire or flooding or collapsing. If you never left that one room, and if the walls were thick enough, you might spend your whole life believing the building was a peaceful place. You would be wrong, but you would have no way to know it, because your only evidence would be the quiet around you. That is our situation exactly. We live in the quiet lane, and the quiet lane has convinced us the whole galaxy is a quiet lane. Let me give you the first reason our address is so unusually safe, because it will set the pattern for everything that follows. The space immediately around the sun is emptier than the galactic average. We're sitting inside a kind of hollow, a cavity in the gas that fills the space between stars, and inside this cavity the gas is far thinner than it is in most of the galaxy. Astronomers call it the local bubble, and it is roughly 1,000 light-years across. We will spend the next part of our journey inside it, understanding how it formed, because the way it formed is the first genuinely unsettling thing you will learn tonight. But for now, just hold this fact. The emptiness that makes our sky look clean and calm is not the normal condition of the galaxy. It is a bubble, and something blew it clear. Think about what it means that our safety comes from emptiness. On Earth we associate safety with shelter, with walls and roofs and the presence of things around us. But out here, in the space between stars, the opposite is true. The dangerous places are the crowded ones, the ones full of gas and dust and other stars, because those are the places where things collide and collapse and explode. The safe places are the empty ones, and we live in an unusually empty place, a cleared-out pocket, which is exactly why nothing has reached in to disturb us for a very long time. The moment we leave this pocket, we lose that protection, and the protection is the only reason we're here to notice its absence. I want to be careful with you tonight because this is not a channel that traffics in fear for its own sake. The point of this journey is not to frighten you. The point is something stranger and, I think, more worth staying awake for, or drifting off to, whichever you prefer. The point is that the universe is far more interesting than the calm sky suggests, and the interest and the danger turn out to be the same thing. The forces that could sterilize a planet are the same forces that built the planet. The crowding that makes stability impossible is the same crowding that makes new stars. To understand why the galaxy gets scarier the further you travel is to understand what the galaxy actually is, underneath the gentle appearance, and what it actually is happens to be one of the most remarkable machines in existence. So let us set out. Picture yourself leaving the surface of the Earth, rising up through the thin shell of air, past the point where the sky turns from blue to black in the middle of the day. Picture the planet shrinking beneath you until the oceans and continents blur into a single bright marble, and then that marble shrinking until it is a pale dot, and then that dot vanishing entirely into the glare of the sun. This is the first step, and it is the easy one, because everything out to here is home, and home still feels safe. But we're going much further than this. We're going to the edge of the sun's reach, and then past it, into the true dark, and then across the arms of the galaxy where stars are born and destroyed, and inward toward the crowded centre, toward the thing that sits at the heart of everything and pulls the whole structure into its slow turning. Keep the quiet lane in your mind as we go. Keep the feeling of standing under that soft band of light, believing it was peaceful, because we are going to travel until that feeling is gone, and then, at the very end, we're going to come back to it, and you are going to look up at the same sky you looked up at tonight, and it is going to mean something completely different. The band of light will not have changed. Only you will have changed because you will finally know what you are looking at. Let us begin the walk outward, and let us start with the bubble we are passing through and how it was carved out of the dark by the deaths of stars. The emptiness around us has a history, and that history is written in the deaths of stars. For a long time, astronomers noticed something odd about the gas in our immediate neighbourhood. The space between stars is not truly empty. It is filled with a thin haze of gas and dust, atoms drifting in the dark, and the density of that haze varies from place to place. In most of the galaxy, near the plane where the sun lives, there is a certain amount of this material, enough to dim distant starlight, and enough, in the denser patches, to eventually collapse into new stars. But right around the sun, the gas thins out dramatically. We sit in a hole. The gas here is about 1/10 as dense as the galactic average, and it is also strangely hot, heated to temperatures far above the cold clouds that fill most of interstellar space. Something had to clear this hole and heat it, and the answer, worked out over decades and sharpened by measurements in the last few years, is both simple and unsettling. The hole was blown by exploding stars. When a massive star reaches the end of its life, it does not fade quietly. It collapses and detonates in a supernova, one of the most violent events the galaxy produces, briefly outshining billions of ordinary stars and hurling its outer layers into space at thousands of kilometers per second. The shock wave from such an explosion sweeps up the surrounding gas, pushes it outward, and leaves behind an expanding cavity of hot, thin material. Our local bubble is the combined cavity left by a whole series of these explosions. In 2022, a team of astronomers published a careful reconstruction of how this happened, and the picture they assembled is worth sitting with. They traced the young stars and star-forming regions near the sun and found that almost all of them sit on the surface of the local bubble, like droplets of water clinging to the inside of an expanding balloon. Working backward, they concluded that the bubble was carved by roughly 15 supernovae, beginning about 14 million years ago. 15 stars over millions of years, each one exploding and adding its shock to the growing cavity, sweeping the gas outward and piling it up into a shell where new stars are now being born from the compressed material. We live inside the hollow those explosions left behind. The shell of that hollow is not an abstraction either, because we can now see it. The compressed gas swept up on the surface of the local bubble is exactly where new stars are forming today. And in recent years, astronomers have traced a great wave of star-forming clouds threading through our neighbourhood, a rippling chain of gas thousands of light-years long, sitting right along the bubble's rim. When you map the young star clusters nearest to the sun, they do not scatter randomly through space. They line up on the surface of the bubble, like frost gathering on the inside of a balloon, because the same explosions that cleared our cavity also piled the gas into a shell dense enough to collapse into the next generation of stars. The local bubble is not just an empty hole. It is a factory wall, and we are sitting in the cleared space at its centre, watching from the inside the aftermath of the process that will build the suns that come after ours. Now here is the part that should make you sit up, or perhaps settle deeper, depending on how you take these things. The sun did not make this bubble. The sun is not the source of these explosions, and the sun has not been sitting in the centre of this cavity for its whole life. The Sun is simply passing through. Our star is on its own orbit around the galaxy, and that orbit has carried it into the local bubble only within roughly the last 5 million years. We wandered in. We are tourists in this emptiness, drifting across a cavity that other stars blew open long before us, and we will eventually drift out the other side and back into denser gas. The clean, calm sky you saw tonight is the view from inside a cavity we happen to be crossing, and the crossing is temporary. Let that reframe the peaceful band of light overhead. The reason you can see so many stars, the reason the night looks so clear and so open, is partly that the gas around us has been swept aside by the deaths of massive stars. If we were sitting in one of the denser regions of the galaxy, buried in a thick cloud of gas and dust, the sky would be dimmer, hazier, the distant stars smeared and reddened. Our unusually good view is a side effect of nearby explosions. The very clarity that makes the galaxy look gentle is the fingerprint of its violence. The window is clean because something shattered the walls. We can even find the debris of these old explosions on Earth, which is where this stops being abstract. Supernovae forge heavy elements and blast them into space, and among those elements is a particular radioactive form of iron called iron-60. Iron-60 is not produced in any ordinary process on Earth, and it decays away over a few million years, so if you find it in ancient layers of rock, it had to have arrived from outside recently in cosmic terms, and we do find it. Deposits of iron-60 have been discovered in the crust at the bottom of the oceans, and even in samples brought back from the surface of the Moon. The amounts and the timing point to one or more supernovae exploding within roughly 300 light-years of us, about 2 to 3 million years ago. Imagine that. 2 to 3 million years ago, as the first members of our own genus were walking upright across the plains of Africa, the light of a dying star would have swelled in their night sky, brightening over days into something that rivaled the Moon, burning there for weeks before slowly fading. And the material from that explosion, the atoms cooked in the star's final collapse, drifted across hundreds of light-years of space and settled, eventually into the mud at the bottom of Earth's oceans, where we dug it up and identified it. The deaths of stars are not distant rumours. They are physically present in the ground beneath the sea. They are part of the record of our planet. Here is the reassuring half of the picture, because I promised you honesty, and not just dread. A supernova at 300 light-years is far enough away to be harmless. It brightens the sky and seeds the region with heavy elements, but it does not damage the biosphere. The danger radius for a supernova, the distance within which the burst of radiation could seriously harm life on a planet, is estimated at somewhere between 25 and 50 light-years. 300 is comfortably outside that. So the explosions that blew our bubble were close enough to clear the gas and drop iron into our oceans, but not close enough to hurt anything living. We got the benefits of the emptiness without the wound. That is the kind of narrow luck we're going to keep finding tonight, and it is worth noticing how narrow it is. Because notice what the local bubble really tells us. It tells us that our peaceful emptiness was made by events that, if they had happened just a little closer, would have been lethal. The same supernovae that cleared our sky and made our view so clean would have stripped the ozone from Earth's atmosphere and bathed the surface in ultraviolet radiation had they gone off within a few dozen light-years instead of a few hundred. Our safety is not the absence of danger. It is danger that happened to occur at a safe distance. The bubble is a scar from a battle we were close enough to witness and far enough to survive, and we have been living in the quiet crater ever since, mistaking the crater for a garden. And ours is not the only such crater. The galaxy is riddled with these bubbles, cavities blown by supernovae and by the fierce winds of massive stars, overlapping and intersecting throughout the disk. In some models, much of the space between the stars near the galactic plane is a froth of such hollows, a foam of cavities carved by generations of dying stars, with the denser gas swept into the walls between them. Our local bubble is simply the one we happen to be inside. It connects to neighbouring cavities, and over millions of years, as the Sun continues its orbit, it will drift out of this one and eventually into another, or into the denser gas of a wall between them. The clean empty pocket we enjoy tonight is one cell in an enormous honeycomb of blown-out spaces, and the honeycomb itself is the record of how many stars have lived and died in our part of the galaxy. Emptiness, out here, is not the original state of things. Emptiness is what violence leaves behind. The Sun's motion through all of this is worth holding on to, because it is the theme of the whole journey. We are not anchored. We are not protected by a permanent shelter. We are moving constantly through a changing environment, and the pleasantness of our current surroundings is a matter of where we happen to be right now on a journey that lasts hundreds of millions of years. Right now, we are in a cleared bubble. In the past, we were in denser gas, and in the future we will be again. The calm is a phase, not a state. If you could speed up time and watch the sun cross the galaxy over hundreds of millions of years, you would see it plunge in and out of clouds, brush past the shockwaves of explosions, rise and fall through the crowded plane of the galaxy, and the conditions around it would swing between clean emptiness and thick, dangerous fog. Tonight is a clean stretch. Tonight is a good night. But tonight is not the rule. So we have taken our first real step, and already the sky has changed meaning. The emptiness is not peace. It is the aftermath of explosions, a temporary clearing we are passing through, littered with the debris of dead stars, some of it lying in our own ocean floor. Keep that in mind as we go further, because the pattern is going to repeat and intensify. Every layer of protection we peel back is going to turn out to be luck, or timing, or distance, rather than any real guarantee. And we have barely left home. We are still inside the sun's own reach, still inside the region the sun can call, in some sense, its territory. In the next part, we are going to travel to the very edge of that territory, to the place where the sun finally loses its grip and hands us over to the galaxy itself. And we are going to find that the edge of the sun's reach is much, much farther away than you have ever been told. Ask most people where the solar system ends, and they will picture the outermost planet, Neptune, and stop there. Neptune orbits at about 30 times the distance between the Earth and the Sun, a unit astronomers call an astronomical unit. So Neptune is roughly 30 astronomical units out, and light from the Sun, which reaches Earth in about 8 minutes, needs more than 4 hours to crawl out to Neptune. That already feels like an ending. Neptune is dim and cold and slow, the last of the great planets, and beyond it the map seems to go blank. But Neptune is nowhere near the edge of the Sun's reach. To find the true edge, you have to travel outward not 30 times the Earth-Sun distance, not 100 times, but tens of thousands of times, into a region so far out that the Sun itself is no longer a disk in the sky, but merely the brightest star among many. Let me take you there in stages, because the stages matter. The Sun does more than shine. It blows a wind, a constant stream of charged particles flowing outward in every direction, and it carries its magnetic field along with that wind. Together they inflate an enormous bubble around the Sun, a region where the Sun's influence dominates over the thin gas of interstellar space. This bubble is called the heliosphere, and its outer boundary, where the solar wind finally loses the pressure to push back the gas beyond, is called the heliopause. We know exactly where it is, because we have sent something through it. The Voyager 1 spacecraft, launched in 1977, crossed the heliopause in August of 2012 at a distance of about 121 astronomical units from the Sun. Its twin, Voyager 2, crossed a few years later. For the first time in history, human machines passed out of the Sun's own bubble and into the space between the stars. But do not let the word crossing fool you into thinking the Voyagers have gone far. They are the fastest and most distant objects humanity has ever launched, moving at about 17 kilometers every second, and they have been traveling outward for nearly half a century. And in all that time, at that tremendous speed, they have covered only a tiny fraction of the distance to the Oort cloud, and a truly negligible fraction of the distance to the nearest star. If Voyager 1 were somehow aimed at Proxima Centauri, which it is not, it would need something like 70 to 80,000 years to get there. 70,000 years at 17 kilometers a second to reach the single closest star. That is longer than the whole span of recorded and unrecorded human history combined. It is a way of feeling, in your body, just how large the gap between stars really is. Our fastest machine, launched before most people alive today were born, has not come close to leaving the Sun's gravitational yard, and it will not reach another star for a length of time that dwarfs the entire existence of our species. The dark between the stars is not a gap you cross. It is a gap you fall into and travel through for ages. You might think that boundary is the edge of the solar system, and in one sense it is. Past the heliopause, you're in interstellar plasma. The Sun's wind no longer reaches you, but the Sun's gravity reaches much, much farther than its wind. And gravity, not wind, is what really defines the Sun's domain. Far beyond the heliopause, Far beyond anything the voyagers will reach for tens of thousands of years lies a shell of icy bodies so distant and so faint that we have never directly seen it, and yet we know it must be there, because we watch pieces of it fall inward. This is the Oort cloud, and it is the true outer territory of the Sun. The Oort cloud is thought to begin somewhere around 2,000 astronomical units from the Sun, and to extend outward to something like 50,000, or even 100,000 astronomical units. Let me translate that, because the numbers are so large they stop meaning anything. 100,000 astronomical units is more than a light year. It is nearly a light and a half. The nearest star to the Sun, Proxima Centauri, is 4¼ light years away. So the outer edge of the Sun's own cloud of comets reaches a substantial fraction of the way to the next star. The Sun's territory and the next star's territory very nearly touch. It is worth pausing on where the comets of the Oort cloud actually came from, because their history is its own quiet warning. They did not form out there in the frozen dark. They formed much closer in, among the giant planets, in the warmer region where there was enough material to build them, and then, early in the solar system's life, the gravity of Jupiter and the other giant planets flung them outward, scattering them by the trillions into enormous distant orbits out to the very edge of the Sun's reach. The Oort cloud is not a native population. It is a cloud of exiles, bodies that were born near the planets and then thrown to the frontier, where they have circled ever since in the dark. Every so often one of them falls back, tumbling in toward the Sun on an orbit that takes millions of years, and we see it blaze into a long-period comet, a visitor from the frontier returning briefly to the warmth before swinging back out into the cold for another million years. The comets that occasionally cross our sky are messengers from the very edge of the Sun's domain, and they carry in their long, slow falls the record of how loosely that edge is held. When you picture the solar system as a tidy set of planets around a star, you are picturing a tiny bright dot at the centre of a domain so large it almost brushes its neighbours. Inside the Oort cloud drift trillions of icy bodies, the leftover crumbs of the solar system's formation, flung out to these enormous distances long ago and left to circle in the cold and the dark. They are so far from the Sun that they take millions of years to complete a single orbit, and they are so loosely held, so far out on the edge of the Sun's gravitational grip, that they can be disturbed by things the inner solar system never feels. A passing star drifting by at a light year or two can tug on the outer Oort cloud and shake loose a rain of comets, sending them tumbling inward toward the Sun over the following millions of years. The gentle tide of the galaxy itself, the collective pull of all the other stars and gas, is strong enough at these distances to matter. Out here, at the edge of the Sun's reach, we are no longer sheltered from the galaxy. We are exposed to it. We can even name a star that is coming. A small dim star called Gliese 710 is currently about 62 light-years away, and it is heading roughly in our direction. In about 1,300,000 years, it will pass through the outer Oort cloud, coming within perhaps 10,000 astronomical units of the Sun. It will not hit anything, it will not collide with a planet or the Sun, but its gravity will stir the outer cloud, nudging comets from their long, slow orbits, some of which will fall inward over the following ages, brightening in Earth's sky as they near the Sun, a few possibly crossing the paths of the inner planets. The galaxy has already dispatched a star toward the edge of our home, and it is on its way, and the only reason it feels like no threat at all is that it will not arrive for more than 1,000,000 years. Let me slow down and take you all the way out there, because I want you to feel the strangeness of this place before we leave it behind. Imagine riding outward on a single comet, one icy body among the trillions, drifting at the outer edge of the Oort cloud, more than a light year from the Sun. Look back the way you came. The Sun is there, but it is no longer the Sun you know. It is not a disk. It casts no warmth, no light you could read by. It is simply the brightest star in a sky that is otherwise identical to the interstellar night, a single yellow point slightly outshining its neighbours, and if you did not already know which star it was, nothing would mark it as special. The planets are long gone, invisible, lost in the glare of that one bright point. The warmth of Earth, the blue of its oceans, the entire world that built you, has collapsed into a pinprick you would struggle to find. And yet, technically, you are still home. You are still, by the reckoning of gravity, inside the Sun's domain. This is where the solar system quietly stops meaning anything, out here in a dark so complete that the Sun is just another star, and there is no line, no wall, no sign to tell you the exact moment you left. That absence of a line is the truly unsettling thing. On Earth, borders are marked. You cross a river, a fence, a mountain range, and you know you have gone from one place to another, but the sun does not let go all at once. Its grip simply fades, gradually, over tens of thousands of astronomical units, until at some ill-defined distance the pull of the galaxy exceeds the pull of the sun, and you have, without any moment of transition, become a possession of the galaxy rather than the star. Astronomers estimate this true gravitational edge, the sun's Hill sphere, at something like 1 to 2 light-years. Past it, an object no longer orbits the sun in any meaningful sense. It orbits the centre of the galaxy, 26,000 light-years away, on the same enormous loop the sun itself is riding. So consider what we have found just by travelling to the edge of home. The sun's reach is far larger than the planets suggest, extending more than a light-year in every direction, nearly touching the next star. But that same enormous reach means the edge of our home is not protected. It is stirred by passing stars, pulled by the tide of the galaxy, and populated by trillions of loosely held bodies that can be knocked loose and sent falling toward us. The further out you go from the warm inner planets, the weaker the sun's grip becomes, and the more the galaxy is allowed to reach in. This is the first appearance of the pattern that will define everything from here on. To travel out is to stop being protected. Say it to yourself as we go, because we are going to see it again in a far more violent form. To travel out is to stop being protected, and we have not even left the sun's territory yet. We have only reached its edge. In the next part, we are going to cross that edge for real, past the last comet of the Oort cloud, out into the true space between the stars, where the sun is finally just a star and nothing shelters you at all. That space is the emptiest environment you will ever encounter, and it is precisely because it is so empty that it holds one of the loneliest and strangest kinds of object in the entire galaxy. We're going into the dark between, and we're going to find that the dark is not as empty as it looks. We have crossed the last edge of the sun's reach, and now, for the first time, we are truly outside. The sun is behind us, one star among the field, and ahead of us stretches the space between the stars, the interstellar medium, the dark that fills the overwhelming majority of the galaxy. This is the part of the galaxy nobody pictures when they look up, because you cannot see it. When you look at the night sky, your eye is drawn to the bright points, the stars, and you skip over the black spaces between them as if they were nothing, as if they were empty. But those black spaces are not nothing. They are almost everything. The stars are the rare exceptions, tiny islands of light and heat scattered across an ocean of dark, and we have just sailed out into that ocean. Let me tell you what the dark is actually made of, because it is emptier than you can easily imagine and yet not truly empty. The space between the stars contains gas, mostly hydrogen, at an average density of about 1 atom per cubic centimetre. 1 atom in a volume the size of a sugar cube. To put that in human terms, the best vacuum we can create in a laboratory on Earth, using our finest pumps, still contains far more atoms per cubic centimetre than interstellar space does. The gas between the stars is a better vacuum than anything we can manufacture. If you held out your hand and swept it through a cubic metre of interstellar space, you would gather up perhaps 1 million atoms, which sounds like a lot until you remember that a single breath of ordinary air contains more atoms than there are stars in the observable universe. The dark between the stars is empty almost beyond comprehension, and yet it is not featureless. Threaded through that thin gas are magnetic fields, invisible lines of force that shape the motion of charged particles across light years. Drifting through it are grains of dust, tiny particles of carbon and silicate, the soot and sand of the galaxy, which dim and redden the light of distant stars. And racing through it, at nearly the speed of light, are cosmic rays, atomic nuclei that were accelerated to tremendous energies by the shock waves of distant supernovae and now stream through interstellar space in every direction. When you left the heliosphere behind, you also left behind the sun's shielding of these cosmic rays. Inside the sun's bubble, the solar wind and magnetic field deflect a large fraction of the galactic cosmic rays before they reach the inner planets. Out here, there is no such shield. The full flux of the galaxy's high-energy radiation passes through you unimpeded. The dark is not only cold and empty, it is irradiated. Try to hold the true proportion of it in your mind, because it is the proportion, more than any single fact, that makes interstellar space so unlike anything in our experience. If you shrank the sun down to the size of a single grain of sand, the nearest other grain of sand, the nearest star, would be several kilometers away, with nothing but empty dark in between. That is the real texture of the galaxy. It is not a crowd of stars. It is a scattering of sand grains separated by kilometers of nothing, and the nothing is the main thing, the stars merely the rare specks within it. When you look up and see the sky full of stars, you are seeing an illusion created by distance, all those far-flung grains gathered by perspective into what looks like a crowded ceiling. Travel out among them, and they spread apart into the isolated, lonely points they truly are, each one separated from the next by an ocean of empty, cold, irradiated dark that would take a machine like the Voyager's tens of thousands of years to cross. It is also, genuinely, cold. Far from any star, the only warmth is the faint background glow left over from the birth of the universe itself, a bath of microwave radiation that fills all of space at a temperature of about 2.7 degrees above absolute zero. Absolute zero is the coldest temperature possible, the point at which atomic motion nearly ceases, and interstellar space far from any star sits just a few degrees above it. Anything drifting out here, with no star to warm it, cools until it is nearly as cold as the universe can be. And that brings us to the strangest inhabitants of the dark, the objects that make interstellar space not just an emptiness to cross, but a place with its own residence and its own kind of loneliness. There are planets out here, not orbiting anything, just drifting, alone, through the space between the stars with no sun to light them or warm them, wandering the dark at whatever speed they were moving when they were set loose. Astronomers call them rogue planets, or free-floating planets, and for a long time they were only a theoretical possibility. But surveys designed to catch the faint gravitational signature of unseen objects have found them, and the counts suggest they are common. Estimates range from billions to as many as trillions of rogue planets across the galaxy. Some studies have suggested that rogue planets may actually outnumber the stars. Think about that. There may be more planets wandering alone in the dark, bound to no star, than there are stars shining in the entire galaxy. Where do they come from? Some were probably born the way normal planets are, in a disk of gas and dust around a young star and then thrown out. Planetary systems, in their early days, are chaotic places. Planets tug on one another, and sometimes one planet's gravity flings another out entirely, ejecting it from its home system at high speed, casting it into the dark forever. Others may have formed alone, condensing directly out of a collapsing cloud of gas without ever having a star to call their own. Either way, the result is the same. A world, possibly the size of Earth, possibly larger, drifting through interstellar space at a temperature just a few degrees above absolute zero, its surface frozen solid, its sky empty of any sun, lit by nothing but the distant, uncaring stars. Consider what it would be like to stand on such a world. There would be no day. There would be no sun to rise, no warmth on your face, no blue sky. The brightest object overhead might be a nearby star, a single bright point no more useful for light than Venus is in our own sky. The ground would be frozen harder than any ice on Earth, and it would stay that way forever, because nothing is ever going to warm it. And this world would be moving silently through the dark on a journey with no destination, having left its birthplace behind long ago and heading toward nothing in particular for billions of years. There may be 1 trillion such worlds in our galaxy alone. The dark between the stars is not empty. It is full of frozen, sunless planets, and we would never see a single one of them coming. Because that is the other thing about the dark. It hides. A rogue planet emits almost no light. It is frozen, dim, and radiating only the faintest heat. One could pass through the space near our solar system, drifting between us and the nearest stars, and unless it happened to pass directly in front of a bright star and bend its light in just the right way, we would have no way to detect it. The dark between the stars is not just a place we cannot see across. It is a place that could hide an entire world a short distance from us and keep it hidden indefinitely. The emptiness is not reassuring. The emptiness is a curtain. The cosmic rays deserve a second look too, because they are the clearest sign that the dark is not passive. These are not rays of light. They are pieces of atoms, the bare nuclei of hydrogen and heavier elements, stripped of their electrons and accelerated to nearly the speed of light by the shock waves of distant supernovae. They come from every direction, a constant sleet of high-energy particles washing through interstellar space, and they carry enough energy that a single one of them can damage the delicate molecules of a living cell. On Earth, we are shielded from most of them, first by the sun's magnetic bubble, and then by our planet's own magnetic field and thick atmosphere. Out here, in the open dark between the stars, there is no shield at all. A traveller crossing interstellar space, or a world drifting through it without a magnetic field to protect it, would be exposed to the full flux, a slow, ceaseless rain of radiation that never stops and never thins. The dark between the stars is not merely empty and cold. It is quietly, invisibly, radioactive, and it has been that way in every direction for billions of years. We do get occasional proof that things move through the dark between stars, because sometimes they pass through our own solar system. In 2017, astronomers detected an object moving through the inner solar system on a path that could only have come from interstellar space. It was named Oumuamua, and it was the first confirmed visitor from beyond the Sun's reach, a chunk of material from another star system passing briefly through ours before continuing on into the dark. 2 years later, in 2019, a second interstellar visitor was found, a comet from beyond named Borisov. These objects proved something we had long suspected. Material routinely crosses between the stars. The first of them, Oumuamua, was strange enough to deserve a moment of its own. It was small, a few hundred meters long, and it appeared to be oddly elongated, tumbling as it passed, and it was moving far too fast on a path far too steep to belong to our Sun. It came in from the direction of interstellar space, swung around the Sun, and left again, never to return, and we caught it only for a few weeks before it faded beyond the reach of our telescopes. It had been travelling through the dark between the stars for who knows how long, millions or billions of years, drifting from some other star system, before it happened to pass through ours during the brief window in which we had telescopes capable of noticing it. For most of the history of life on Earth, objects like this would have passed through the solar system completely unseen. We have only just developed the ability to catch them, and the moment we did, we found them, which strongly suggests they have been coming through all along, unremarked, for the entire existence of our planet. The galaxy is not a set of isolated islands. Things move between them, drifting out of one star's domain and through the dark and into another's, and occasionally one of them passes close enough for us to notice. So the dark between the stars, which looked like the emptiest and therefore the safest place we could be, turns out to be its own kind of unsettling. It is irradiated by cosmic rays with no shield to stop them. It is cold almost beyond measuring. It is full of frozen, sunless worlds that outnumber the stars and that we cannot see, and it hides its contents so completely that an entire planet could drift past us unnoticed. This is the ocean that fills most of the galaxy, and we have only just entered it. We are still, remember, extremely close to home in galactic terms, still among the Sun's near neighbours, still in a quiet, ordinary stretch of the galaxy's outskirts, and already the emptiness has stopped feeling safe. Now we are going to travel far enough that the stars begin to gather, that the gas begins to thicken, that we approach the great structures of the galaxy where stars are made. We are heading for the spiral arms, and in the spiral arms the dark is going to give way to light, and the light is going to be far more dangerous than the dark ever was. If you have ever seen a photograph of a spiral galaxy, a great pinwheel of light with luminous arms curling out from a bright centre, you have seen what our galaxy looks like from the outside, more or less. We cannot photograph the Milky Way that way, because we are trapped inside it, but we have mapped it well enough to know that it is a barred spiral, with a straight bar of stars across its centre and arms winding outward from the ends of the bar. Those arms are the galaxy's most beautiful feature, and they are the reason we are now going to trade the loneliness of the dark for a different and worse kind of fear, because the spiral arms are where the galaxy makes its stars, and making a star and destroying a world turn out to be the same activity, happening in the same place. Let me first correct something you probably believe about the arms, because the truth is stranger, and it matters for what follows. You might imagine the spiral arms as fixed streams of stars, like the trailing arms of a spinning firework, with each star locked into its arm and riding around with it. But that is not how they work. The arms are not made of the same stars over time. They are density waves, patterns of compression that move through the galaxy at their own speed, and stars flow into them and out of them, the way cars flow into and out of a traffic jam. The traffic jam stays in roughly the same place on the highway, but the individual cars are always changing, entering the jam from behind, crawling through the crowded region, and speeding away once they clear the front. In the same way, a spiral arm is a region where matter piles up as it orbits the galaxy, and stars and gas pass through it, spending a while in the crowd before moving on. Now, why does the pileup matter? Because when gas gets compressed, it collapses, and when gas collapses, it forms stars. The spiral arms are regions where the thin gas of the galaxy gets squeezed together, dense enough to fall in on itself under its own gravity, and ignite into new suns. The arms are, quite literally, the galaxy's nurseries. Every star you can see, including the Sun, was born in a region like this, out of a collapsing cloud of gas, in the crowded lanes of a spiral arm. The arms glow brightly, brighter than the rest of the disk, precisely because they are full of freshly minted stars, including the most massive and luminous kinds, the hot blue stars that burn thousands of times brighter than the Sun. And here is where the beauty turns. Those hot, massive, brilliant blue stars, the ones that make the arm shine, do not live long. A star like the Sun burns steadily for about 10 billion years. But the most massive stars, the giants that light up the spiral arms, burn through their fuel in only a few million years, a cosmic eye blink, and then they die as supernovae. So the spiral arms are not just nurseries. They are also, at the very same time and in the very same places, the galaxy's execution grounds. The gas collapses, the massive stars ignite, they blaze for a few million years, and then they detonate, blasting the surrounding region with radiation and shock waves, seeding new collapses that form new stars which will in turn explode. Creation and annihilation are not separate events in the arms. They are a single ongoing process. The arms make stars and unmake worlds in the same breath. Our own galaxy has several of these arms, and they have names, though we're still learning their exact shapes because we're trying to map them from the inside. There is the Perseus arm and the Sagittarius arm, the major spiral features winding through the disk, and between them and closer to us lies a smaller feature, a minor arm or spur, and this is where the Sun sits. It is sometimes called the Orion arm, or the local spur, and it is not one of the grand structures. It is a lesser lane, a bridge of stars between two of the great arms, and our position in it is another piece of the quiet luck we keep uncovering. We are not buried in the crowded heart of a major arm, where the massive stars cluster and the supernova fire most often. We are off to the side in a gentler spur, watching the great arms from a comfortable remove. The bright star-forming regions we can point to in the night sky, the glowing clouds where new suns are igniting, are mostly at a safe distance, in the major arms, not in our own quiet lane. The massive stars that light the arms tend to be born in groups, in what astronomers call associations, dozens or hundreds of hot young giants forming together out of the same collapsing cloud. And because they are all massive, they all die young, and they die close together in time and space. An association of massive stars is a cluster of countdowns, each one ticking toward its own supernova, and over a few million years they detonate one after another, a chain of explosions in the same region, each adding its shock to the gas, driving new collapses, carving new bubbles, seeding new stars. The arms are not lit by steady, patient suns like ours. They are lit by brilliant, short-lived giants that burn furiously and die in bursts, and the light we admire from a distance is the glow of a region in a constant state of ignition and detonation. This is the moment to say something that should genuinely change how you feel about your own existence. You are made in a place you could not survive today. Every atom of iron in your blood, every atom of calcium in your bones, every atom of oxygen you are breathing right now was forged inside a massive star and scattered into space by a supernova. The material that became the Sun, the Earth, the oceans, and you was gathered from the enriched wreckage of earlier stars that lived and died in the crowded, radiation-soaked lanes of the spiral arms. You are the product of stellar violence. The Sun itself was born this way, in a crowd, and it did not begin alone. Stars form in clusters, dozens or hundreds or thousands of them, condensing together out of the same collapsing cloud, and our Sun was one of a family, surrounded at its birth by hundreds of sibling stars formed from the same gas at the same time. We do not know exactly how many, but we know they existed, because that is how stars are made, and we know they're gone now, scattered. Over the 4.5 billion years since, the gentle differences in their orbits carried the Sun's siblings away from it, spreading them around the galaxy until they were lost among the hundreds of billions of other stars. Somewhere out there, right now, are stars born from the very same cloud as our Sun, chemical siblings of the star that lights our sky, and we cannot pick them out. The Sun's birth family has been dispersed across the whole galaxy, and the Sun rides alone now, in its quiet lane, with no memory and no trace of the crowd it came from. Even our own origin is a story of a crowd that scattered, a nursery that emptied, a family the galaxy pulled apart and spread thin across 100,000 light-years. And if you were to travel back into one of those active star-forming regions today, into the crowded arm where the process is still running, you would find it lethal, bathed in the ultraviolet glare of young massive stars and periodically ripped by the shock waves of their deaths. The place that made you would kill you. That is not a contradiction. That is simply what a galaxy is. Let me put you inside one of these regions for a moment, because it is one thing to describe it and another to stand in it. Imagine a world orbiting a star only 30 light-years from a massive blue giant that is nearing the end of its life. For most of that world's history, the giant is simply a very bright star, a beautiful blue-white point far brighter than any other in the sky, but still just a point, still just decoration. Then, one ordinary night, something changes. The point begins to brighten. Over hours, then days, it swells from a bright star into something impossible, something that hurts to look at, a second source of light in the sky that rivals the world's own sun. It does not move, it does not set, it simply hangs there, in the middle of what should be night, casting shadows, turning darkness into a strange blue twilight. It is the death of the giant, arriving at the speed of light, and from 30 light-years away it is close enough to matter. The sky itself has become a weapon, and there is nothing anyone on that world could do but watch it burn. That is the danger of the middle distances, and we will return to it in a moment, because it is the heart of the next part of our journey. For now, hold on to the reframing of the arms. The arms are where the galaxy is most alive, and being most alive means being most dangerous. The Sun's great fortune, one of the several pieces of narrow luck that have kept us here, is that its orbit does not carry it repeatedly and violently through these arms. The Sun moves through the galaxy at close to the same speed as the spiral pattern itself, near what astronomers call the co-rotation radius, the special distance at which a star and the density wave keep pace. Because we move at nearly the pattern's speed, we cross the arms relatively rarely and gently, rather than ploughing through them again and again the way stars at other distances do. We spend most of our time in the calmer spaces between the arms, in stretches like the one we occupy now. Think about how thin that thread of safety is. If the Sun orbited a little faster or a little slower relative to the spiral pattern, it would pass through the crowded, explosive arms far more often, and each passage would expose the solar system to denser gas, more radiation, and a higher chance of a nearby supernova. The stability that has allowed life on Earth to develop over billions of years may depend, in part, on the accident that our star happens to orbit at nearly the co-rotation radius, keeping step with the arms rather than crashing through them. Once again, our safety is not a wall. It is a coincidence of motion, a matter of orbiting at just the right speed to avoid the dangerous places, and it holds only as long as that coincidence holds. So the galaxy is not a place. The galaxy is a machine. It takes in thin gas and compresses it in the turning lanes of its arms and forges stars, and it burns those stars and it detonates the largest of them, and it uses the wreckage to forge the next generation, over and over, for billions of years. We are one product of that machine, thrown clear of the worst of it, riding a quiet orbit through the calmer gaps. But we came from the machine, and the machine is still running, all around us, and if we travel into the parts of it that are most active, the parts that are making the most light, we find the parts that would most easily destroy us. The galaxy is not a place, it is a machine. Remember that as we go inward, because the machine gets more intense with every step toward the centre, and the next step takes us into the range where its violence has, in the past, very nearly reached us. We are going to look at the middle distances, at supernovae and the bursts of radiation that can cross thousands of light-years, and at the narrow band of the galaxy where life might actually be possible. And we're going to find that death has already come closer than you think. Let us stop for a moment and stand still, roughly halfway through our journey, and look back at the road we have travelled, because it is worth putting the pieces together before we go any further, and because the middle of a long walk is a good place to catch your breath. We began under a peaceful sky, and we learned that the peace was the view from inside a cavity blown clear by dead stars. We travelled to the edge of the sun's reach and found that the edge is more than a light year away and is stirred by passing stars. We crossed into the dark between the stars and found it cold, irradiated and full of frozen sunless worlds we cannot see, and we entered the spiral arms and found that the places where the galaxy makes its stars are the same places where it destroys worlds. Each step took away a layer of protection and revealed a little more of the machine underneath. Now we're going to look at the danger that does not need us to travel to it at all, the danger that can cross the empty distances and reach us where we stand. The clearest example is the supernova, the death of a massive star which we have already met at the edges of the spiral arms. When a star many times heavier than the Sun exhausts its fuel, its core collapses in less than a second, and the outer layers rebound in an explosion that, for a few weeks, shines with the light of billions of ordinary stars. If such an explosion happened close enough to Earth, it would be catastrophic, not because of the light, but because of the radiation. A nearby supernova would flood the Earth with gamma rays and, over the following years, with cosmic rays, and these would tear apart the ozone layer that shields the surface from the sun's ultraviolet light. Strip away the ozone, and the ultraviolet radiation reaching the ground would rise sharply, damaging the base of the food chain, the tiny organisms in the oceans and the plants on land, with consequences that could ripple upward into a mass extinction. The estimated danger radius for a supernova is somewhere between 25 and 50 light-years. Within that distance, a stellar death could wound the entire biosphere. Now recall what we learned from the local bubble. The iron 60 in our ocean floors and in the moon's soil tells us that one or more supernovae exploded within about 300 light-years of Earth, roughly 2 to 3 million years ago. 300 light-years is safely outside the danger radius, so those explosions did not sterilize the planet. But sit with the arithmetic for a moment. The danger radius is 25 to 50 light-years. The explosions we can physically detect in our own geological record happened at 300. That is a comfortable margin, but it is not an infinite one, and the same process that put those explosions at 300 light-years could, on another roll of the dice, have put one at 40. There is nothing special protecting Earth from a nearby supernova except the current arrangement of massive stars in our neighbourhood, and that arrangement changes over millions of years as stars are born, drift and die. There is worse, and it can reach much further. Certain rare stellar deaths produce gamma-ray bursts, the most energetic explosions the galaxy makes, in which the dying star channels an enormous fraction of its energy into two narrow beams of gamma rays fired out along its axis. A gamma-ray burst concentrates its power so tightly that it can be dangerous from thousands of light-years away if one of its beams happens to be pointed at you. The odds of any particular burst being aimed at Earth are small, because the beams are narrow and the galaxy is large. But over the enormous stretch of geological time, the possibility is real. One leading hypothesis, still unproven, suggests that a gamma-ray burst or a nearby supernova may have contributed to the late Ordovician mass extinction, about 445 million years ago, one of the largest die-offs in the history of life on Earth. We cannot confirm it. But the fact that it is even a serious scientific hypothesis tells you something. The galaxy contains explosions powerful enough that, from thousands of light-years away, they remain a candidate cause for the near erasure of life. It is worth understanding how a burst of radiation from so far away could reach down and touch life on the ground, because the mechanism is not what you might expect. The gamma rays themselves never reach the surface. They are absorbed high in the atmosphere. But when they are absorbed, they tear apart the molecules of the upper air, and in the wreckage they drive chemical reactions that destroy ozone, the thin layer of gas that shields the surface from the sun's ultraviolet light. It is not the burst that kills. It is what the burst does to the atmosphere, and then what the unshielded sun does afterward. For years after a nearby gamma-ray burst or supernova, with the ozone layer stripped away, the ordinary sunlight falling on the planet would carry far more ultraviolet radiation than life at the surface is built to withstand. The tiny organisms at the base of the ocean food chain, the plankton that everything else ultimately depends on, would be damaged first, and the harm would climb upward through every living thing that depends on them. A single explosion, thousands of light-years away, could turn the planet's own sunlight into a slow poison. That is how something so distant can still be deadly. It does not have to reach you. It only has to break the shield between you and the star you already orbit. Let me take you to the ancient shore, because I want this to be more than a number. Picture the coast of Africa, roughly 2.5 million years ago. The first members of our own lineage are alive, small and clever, walking upright, sheltering at night, watching the sky the way every generation has. On one of those nights, they notice a new star. It was not there before. Over the following nights it brightens and brightens, until it is the brightest thing in the sky after the moon, a single fierce point that casts faint shadows on the ground and does not move among the other stars. For weeks it burns, and then, slowly over months it fades, until at last it is gone, and the sky is ordinary again. They could not have known what they were seeing. They could not have known that the light came from a star tearing itself apart hundreds of light years away, or that its invisible cargo of iron would drift across the dark for ages and settle, eventually, into the mud of a sea where creatures not yet imagined would one day dig it up and read it. They only saw a light in the sky, but the light was real, and the star was real, and the distance that saved them was real, and every part of it is written now in the rock beneath the ocean. This is the point in our journey where we should talk about whether any place in the galaxy is actually safe for long enough for life to take hold, because it turns out that this is a genuine scientific question with a genuine and narrow answer. In 2004, a group of astronomers proposed the idea of a galactic habitable zone, a region of the galaxy where the conditions for complex life might be met, and their conclusion was that it is a fairly thin band. Too close to the centre of the galaxy, and the density of stars is high, supernovae are frequent and radiation is intense, so planets are repeatedly disturbed and sterilized before life can develop. Too far out toward the edge, and there are not enough heavy elements because the outer galaxy has seen fewer generations of stars to forge and scatter them, so rocky planets like Earth struggle to form at all. In between lies a habitable band, very roughly 13,000 to 33,000 light-years from the centre. The Sun, at about 26,000 light-years out, sits comfortably within it. Consider how many separate conditions that band requires to line up. A world in the habitable band needs to be far enough from the centre to escape the crowding, the frequent supernova, and the radiation of the inner galaxy, which rules out everything toward the core. But it also needs to be close enough in that its region has been enriched by enough earlier generations of stars to hold the heavy elements a rocky planet is built from, which rules out the thinly populated outer edge, where the gas is too pure, too little processed, to easily make an Earth, and it needs to be on a well-behaved orbit, one that keeps it in that band rather than plunging it repeatedly through the dangerous inner regions or the crowded arms. Every one of those requirements narrows the map. When you overlay them all, the region that satisfies all of them at once is not most of the galaxy. It is a ring, a band, a minority of the whole, and the further a world sits from that band in either direction, inward toward the fire or outward toward the emptiness, the worse its chances become. We are not merely in a good spot. We are in a spot that satisfies a whole list of separate conditions simultaneously, and most of the galaxy fails at least one of them. The idea of the galactic habitable zone is debated, and some later models argue that even the crowded inner galaxy might host more habitable worlds than the simple picture allows, radiation notwithstanding. But the core insight survives the debate, and the core insight is this. Location within the galaxy matters enormously for whether a place can be safe long enough for life. It is not enough to have a planet at the right distance from a star, with liquid water and a stable atmosphere. That planet also has to sit in a part of the galaxy that will leave it alone, that will not fry it with a nearby supernova or strip its outer solar system with a passing star for the billions of years that complex life seems to require. And the parts of the galaxy that will leave a planet alone are a minority of the whole. Most of the galaxy is not the quiet lane. Most of the galaxy is the crowded, radiation-soaked, disturbed majority, and only a fortunate band at the right distance from the centre offers the long calm that life needs. So gather the pieces of this middle stretch of our journey. Supernovae can wound a biosphere from within 50 light-years, and we know from the iron in our oceans that they have exploded within a few hundred light-years of us in our own recent past. Gamma-ray bursts can threaten from thousands of light-years, and one may already have scarred the history of life on Earth. And the region of the galaxy where a planet can stay undisturbed long enough for complex life to arise is only a band, not the whole, and we happen to live inside it. Every one of these facts points the same way. The distances that separate us from disaster are real, but they are not large enough to be comforting, and they have, more than once, already been crossed. Death has reached toward us before and missed, and left its fingerprints in the rock. Now we turn inward again, toward the centre, where the distances shrink and the stars gather, and where the very crowding that fills the sky with light makes the long calm that life needs almost impossible to find. We are going into the crowd. The further inward we travel toward the centre of the galaxy, the more the stars begin to gather. Out where the sun lives, in the quiet suburbs, the stars are spread thin. The nearest star to the sun is more than 4 light-years away, and the stars in our neighbourhood are separated on average by several light-years of empty dark. That spacing is part of why our sky looks the way it does, with individual stars standing apart against the black, each one distinct, none of them close. But as we move inward, that spacing shrinks, and it shrinks not gradually but dramatically. By the time we reach the central regions of the galaxy, the stars are packed together so tightly that the sky, if you were standing on a planet there, would not look like our sky at all. It would blaze. Let me give you the numbers, because the change is difficult to believe. In the central few light-years of the galaxy, the density of stars is not twice what it is near the Sun, or 10 times, or 100 times. It is on the order of millions of times higher. Where the Sun has a handful of stars within 10 light-years, a planet near the galactic centre might have millions of stars within the same distance. The night sky from such a world would be crowded with brilliant points, thousands of them brighter than any star in our sky. The whole heavens washed in a permanent glow so bright that there might be no true darkness at all. No real night, just a sky perpetually lit by the massed light of countless nearby suns. It would be beautiful beyond anything we can see from Earth, and it would be a catastrophe for anything trying to live there. Here is why crowding is deadly, and it is not the reason you might first guess. The danger of the crowded inner galaxy is not that stars collide with each other. Even packed millions of times more densely than our neighbourhood, stars are still tiny compared to the distances between them, and direct collisions remain rare. The danger is subtler and, in a way, worse. In a crowded region, stars pass close to one another frequently, and when a star passes close to another star's planetary system, its gravity disturbs that system. It can strip away the outer planets, fling them into interstellar space, and tear apart the loosely held outer cloud of comets, sending a barrage of icy bodies falling inward toward the inner planets. Remember the Oort cloud, and how a single passing star, more than 1 million years from now, will stir ours from 62 light-years away. Now imagine a region where such close passages are not once in millions of years events but routine, happening again and again over the life of a planetary system. A planet in the crowded inner galaxy cannot count on being left alone. Its orbit, and the orbits of its sibling planets, would be repeatedly jostled by the gravity of passing stars. Its outer solar system would be regularly stripped, and its comet cloud regularly disturbed, sending waves of impacts inward. The long, quiet, undisturbed billions of years that life on Earth enjoyed, the stability that lets simple cells slowly become complex ones, and eventually become creatures that could look up and measure the galaxy, would be nearly impossible to maintain in the crowd. Every few million years, another star would pass close enough to shake the system, to rain comets down, to nudge the planet's orbit. Stability, the one thing life seems to need above all, is exactly what crowding takes away. There is a deeper irony buried in this, and it is worth drawing out. The inner galaxy is not only more dangerous, it is also, in some ways, richer. It has seen more generations of stars live and die, and each generation forges heavy elements and scatters them into the gas, so the inner regions are more enriched with the raw material that planets are built from. In principle, that should make the inner galaxy a good place to build worlds. There is plenty of the right stuff there. And yet the same crowding that made it rich also makes it deadly, because the frequent supernovae and close stellar passages that enrich the gas are the very things that would keep a planet from ever settling into a stable, undisturbed billion-year calm. The inner galaxy is a place with all the ingredients for life and none of the peace. It is a kitchen fully stocked and permanently on fire. Whatever life might begin there would be interrupted again and again before it could grow into anything that lasts, and the disturbances would not always be gentle nudges. In a region packed millions of times more densely than our own, a truly close stellar encounter, a star passing not light years away but at the distance of the outer planets, becomes something that will actually happen over the age of a planetary system. Such a passage would not merely stir the comet cloud, it could rip planets out of their orbits entirely, tearing a world loose from its star and casting it into the dark to join the wandering rogue planets we met earlier. Some of the frozen, sunless worlds drifting through interstellar space were almost certainly made this way, torn from crowded systems by a passing star and exiled into the cold. In the inner galaxy, the line between a planet with a home and a planet cast into the void is thin, and it is crossed by the simple, ordinary fact of living too close to too many neighbours. And it is not only the gravity. The crowded inner galaxy is also bathed in radiation, far more than our sheltered neighbourhood. A denser population of stars means a denser population of massive stars, and massive stars mean more supernovae, more frequent and more nearby, each one flooding the region with radiation. It also means more of the galaxy's most extreme objects. Among the stars near the centre are X-ray binaries, systems in which a dead star, a neutron star or a stellar mass black hole, pulls gas from a living companion. As that gas spirals in, it heats to millions of degrees and blazes in X-rays, filling the surrounding space with high-energy radiation. Scattered through the inner galaxy are neutron stars spinning hundreds of times a second, the collapsed cores of dead giants sweeping beams of radiation across space. The inner galaxy is not just crowded with stars, it is crowded with the corpses of stars, and the corpses are often more dangerous than the living. Let me put you on one of these inner galaxy worlds for a moment, so the crowding stops being a statistic. Imagine standing on a planet only a few thousand light years from the centre, looking up. There is no darkness. The sky is a field of brilliant stars, so many and so bright that they cast light like a perpetual moon, and the band of the galaxy's disk is not a faint river, but a broad, blazing structure filling half the sky. It is the most spectacular view any world could offer, and it is a warning written in light. Every one of those brilliant nearby stars is a gravitational hazard capable of reaching in and disturbing your world if its path brings it close. Some of them are massive enough to explode within your danger radius. Somewhere among them, unseen, are the X-ray binaries and the neutron stars pouring out radiation. You would be living inside the most beautiful and most hostile sky in the galaxy, and the beauty and the hostility would be the same thing. Too many stars, too close. This is the deepening of a pattern we have been tracing all along. Out in the quiet lane, our safety came from emptiness and distance, from the fact that the nearest star is more than 4 light years away, and nothing has reached in to disturb us for a very long time. The inner galaxy has the opposite of that. It is the antithesis of the quiet lane. Where we have space and stillness, it has crowding and constant disturbance, and the galaxy is mostly more like the inner regions than like our sheltered outskirts. The quiet lane is the exception. The crowd is closer to the rule. We're not living in a typical part of the galaxy that happens to be calm. We are living in one of the atypically calm parts, and the typical parts are the ones we have been travelling toward, the ones where stability is impossible and life would struggle to ever begin. At the very centre of the crowd sits its densest concentration of all, a tight knot of stars packed around the galactic core so closely that it forms a distinct structure, a nuclear star cluster millions of times denser than our neighbourhood, one of the most crowded stellar environments in the entire galaxy. Millions of stars are jammed into a region only a few light years across, orbiting one another and the central mass in a slow, grinding swarm. If you tried to build a stable planetary system in that swarm, the constant close passages of neighbouring stars would tear it apart before it could ever settle. Nothing there stays undisturbed for long. It is the opposite of everything life requires, and it sits at the exact centre of the structure we look up at and call peaceful, the innermost and most crowded room of the whole house, and everything else, including our own quiet lane, orbits around it. There is a claustrophobia to this that is different from every fear we have met so far. In the dark between the stars, the fear was loneliness, the horror of a frozen world drifting alone with no sun. Here, approaching the centre, the fear is the opposite. Too much company, too many suns, a sky so full that there is nowhere to hide, and never a moment of being left alone. And both of these fears, the loneliness of the dark and the claustrophobia of the crowd, are simply different regions of the same galaxy, the same structure we look up at on a calm night and call peaceful. We have travelled from the emptiest part to the crowded part, and we are not done, because at the very centre of the crowd, at the point around which all these millions of packed stars are orbiting, there is something else, something the stars are circling, something that has been pulling this entire structure into its slow rotation for as long as the galaxy has existed. We're almost at the centre now, and at the centre waits the single scariest object in the entire galaxy, and we're going to stand as close to it as anything can and watch what it does to the stars that come too near. We have arrived at the centre of the galaxy, and I want to tell you exactly what is here, because it is both smaller and more powerful than anything we have met on the way. At the heart of the Milky Way, at the point around which the entire structure turns, sits a black hole. Not a stellar mass black hole, the kind left behind when a single massive star dies, but something in a different category entirely, a supermassive black hole with a mass of about 4.15 million times the mass of the Sun. Its name is Sagittarius A star, and it is about 26,000 light-years from where you are sitting, which means it is the same distance from you as you are from it, and you have been orbiting it your entire life without ever feeling it. Let me first correct the picture you probably have, because the reality is stranger than the cartoon. When people hear that there is a supermassive black hole at the centre of the galaxy, they imagine an enormous object, something the size of the whole central region, a great dark maw swallowing everything nearby. But a black hole's size is set by its mass, and even 4 million solar masses compressed into a black hole is not physically large. The event horizon of Sagittarius A star, the boundary beyond which nothing can escape, is only about 12 million kilometres across. That sounds like a lot until you compare it to the solar system. 12 million kilometres is smaller than the orbit of Mercury, the innermost planet. The object that anchors the rotation of 100 billion stars, the gravitational hinge of the entire galaxy, would fit comfortably inside the orbit of the closest planet to our own Sun. It is not big. It is dense beyond imagining. 4 million suns crushed into a space smaller than the inner solar system, and its power comes not from its size but from that density. We have actually seen it, which is one of the great achievements of recent science. For decades, the centre of the galaxy was hidden behind thick clouds of gas and dust, invisible to ordinary telescopes. But astronomers found ways around the veil. They tracked the motions of individual stars near the centre over many years, and they watched those stars swing around something massive and invisible, tracing out orbits that could only be explained by an enormous concentration of mass in a tiny volume. That work, patient and painstaking, earned the 2020 Nobel Prize in Physics. And then, in May of 2022, an array of radio telescopes spread across the Earth, working together as a single instrument the size of the planet, produced an actual image of Sagittarius A star, a ring of light bent around a dark central shadow, the silhouette of the black hole itself against the glowing gas swirling around it. We have looked at the thing at the centre of our galaxy, and it looked back as an absence, a hole in the light. Making that image was harder than almost anything astronomy has ever attempted, and the difficulty tells you how strange the target is. A single telescope, even the largest ever built, could never resolve something so small and so far away. So astronomers linked radio telescopes on separate continents, in Chile, in Hawaii, in Spain, at the South Pole, and combined their signals so that they worked together as though they were pieces of one instrument, as wide as the entire planet. Only a telescope the size of the Earth could see detail fine enough to make out the ring of light around a black hole 26,000 light-years away, and even then it took a network of observatories, atomic clocks to keep their measurements in step, and years of computation to turn the raw data into a picture. The result was a blurred orange ring around a dark centre, and it does not look like much at first. But that dark centre is the shadow of the event horizon itself, the region from which no light escapes, printed against the glow of superheated gas swirling around it. It is a photograph of the edge of nothing. Now let me show you what it does to the stars that come near it, because this is where the centre stops being an abstraction and becomes something out of a fever. Around Sagittarius A star orbit a group of stars astronomers call the S stars, and they move in a way no star near the Sun ever moves. One of them, called S2, orbits the black hole once every 16 years. 16 years to loop around the centre of the galaxy, when the Sun takes over 200 million years to make its far larger orbit, and at the closest point of its orbit, when S2 swings in nearest to the black hole, it is moving at about 5,000 kilometres every second. That is nearly 3% of the speed of light. A star, an object like our Sun, whipped around a point of pure gravity at 3% of light speed, close enough that the whole orbit takes less time than it takes a human being to finish growing up. And S2 is not even the fastest. Another star, found more recently and called S4716, orbits in only about 4 years, moving at up to 8,000 kilometers per second at its closest approach. These stars are not drifting. They are being flung around the center like stones on the end of a string, at speeds that would carry them across the entire width of the Sun in a matter of minutes. Let me place you there, at the center, to watch it. Imagine standing at a safe remove from Sagittarius A star, looking toward the point that anchors the galaxy. You see nothing at the center itself, only a darkness where the stars behind should be, ringed by a faint distortion where the light of more distant stars is bent around the hole, and then you see the S stars, and their motion is wrong, unnatural, too fast. S2 comes sweeping in from the dark, accelerating as it falls toward the black hole, faster and faster until it rounds the point of absence at 5,000 kilometers a second. Its path bent into a tight hairpin by gravity so strong it visibly warps the star's course, and then it flings back out into the dark, slowing, climbing away, only to fall again years later. Nothing marks the thing at the center. It gives off no light of its own. You know it is there only by what it does, by the stars bending their paths around it, by the way the whole crowded heart of the galaxy pivots around a point you cannot see. It is the most powerful object for tens of thousands of light years, and it is invisible, and you are looking straight at it. Here is the fact that should genuinely unsettle you, the one that turns the center from a spectacle into a warning. Sagittarius A star is quiet right now. It is feeding slowly, only occasionally drawing in gas, and by the standards of supermassive black holes it is dim and calm. But it was not always calm. Above and below the center of the galaxy, astronomers have found two enormous structures, lobes of hot gas glowing in gamma rays, extending about 25,000 light-years above the galactic plane and about 25,000 light-years below it, roughly 50,000 light-years from tip to tip. They are called the Fermi bubbles, discovered in 2010, and they are almost certainly the fossil of a past outburst. At some point in the relatively recent past, in the last few million years, Sagittarius A star was not quiet. It fed violently, and as it fed it blasted an enormous outpouring of energy out along the axis of the galaxy, inflating these two great bubbles that we still see glowing today. The quiet hole at the center was, not long ago, a roaring one. We have even watched the center get ready to feed, in our own lifetimes. A little more than a decade ago, astronomers tracked a cloud of gas, given the plane name G2, falling towards Sagittarius A star. For a while there was real anticipation that we might see the black hole tear the cloud apart and blaze up as it swallowed the debris, a chance to watch a supermassive black hole feed in real time. In the end, the cloud survived its closest approach mostly intact, stretched and disturbed but not consumed, and the black hole stayed quiet. But the episode was a reminder that the center is not a museum piece. It is an active object, still surrounded by gas and stars falling toward it, and every so often something gets close enough to matter. The next cloud or the next star might not be so lucky, and when one of them finally falls in, the quiet hole at the center of our galaxy will brighten again, exactly as it has before. There is one more strangeness to the center that I cannot leave out, because it changes what the word near even means there. Close to a black hole, gravity is so strong that it warps not only space but time. To an observer watching from a safe distance, a clock near the event horizon appears to tick more and more slowly the closer it gets, until, right at the horizon, it seems to freeze entirely. Time itself stretches and slows in the grip of that much gravity. So the region around Sagittarius A star is not just a place of extreme speed and extreme density. It is a place where the flow of time itself bends, where a moment stretches toward forever at the edge of the hole. The stars whipping past at thousands of kilometers a second are also, in a sense we can barely picture, moving through a landscape where time runs at different rates, depending on how far into the gravity you fall. The center of our galaxy is the one place within reach where the smooth, steady passage of time we take for granted visibly comes apart. We can date one of these episodes with disturbing precision. Evidence assembled in 2019 points to a violent flare from Sagittarius A star about 3.5 million years ago. an eruption that sent a cone of ionizing radiation blasting outward from the center of the galaxy, so powerful that it lit up a stream of gas called the Magellanic Stream more than 200,000 light-years away. 3.5 million years ago. That is not the distant past of the universe. That is within the history of our own lineage. When Sagittarius A star last roared, there were already upright walking ancestors of ours on the plains of Africa. The thing at the center of our galaxy erupted with enough force to illuminate gas hundreds of thousands of light-years away, and it did so while our own family was already alive to have, in principle, seen the center of the sky change. The center is not permanently quiet. It is quiet now on our watch, but it has a history of violence, and its next outburst is not scheduled and not predictable. Let me be honest about the danger, because I promised you I would not manufacture fear. From our safe distance of 26,000 light-years, even a major outburst of Sagittarius A star would most likely not be directly lethal to Earth. The danger from the center, like the danger from a supernova, falls off steeply with distance, and 26,000 light-years is a long way. The worlds truly at risk from the center's violence are the ones near it, the crowded inner galaxy planets we visited a moment ago, which sit within reach of its eruptions as well as its radiation and its gravitational chaos. But sit with the full picture of what the center is. It is a point of pure absence, smaller than the orbit of Mercury, holding 4 million suns, anchoring 100 billion stars, flinging nearby stars around at a substantial fraction of light speed, and periodically roaring with enough force to light up gas across hundreds of thousands of light-years. That is the thing at the heart of the structure you look up at on a calm night. That is what the peaceful band of light is turning around. This is the scariest address in the galaxy, and everything, including you, is orbiting it. And we are still not done, because as terrifying as the center is, there is something even larger surrounding all of it, something that outweighs every star and every black hole combined, and it is completely invisible. Everything we have looked at so far, every star, every cloud of gas, every supernova, the crowded center and the black hole at its heart, all of it together is only a small fraction of what the galaxy actually is. This is perhaps the hardest thing to accept about the Milky Way, and it is certainly the strangest. The bright pinwheel of stars, the thing we point to and call our galaxy, is a minority component of the real structure. The total mass of the Milky Way is something like 1 to 1.5 trillion times the mass of the Sun. But if you add up all the stars, all the gas, all the dust, everything that gives off light or blocks it, everything we can actually see, you account for only a small slice of that total, very roughly somewhere between 5 and 15%. The rest, the overwhelming majority of the galaxy's mass, is something we cannot see at all. We call it dark matter, and the honest truth is that we do not know what it is. Let me be precise about what that means, because it is easy to hear and hard to absorb. When astronomers measured how fast the stars in the outer parts of the galaxy orbit the center, they found something that made no sense. The stars far out on the edge of the disk were moving too fast. According to the gravity of all the visible matter, all the stars and gas we can see, those outer stars should have been moving slowly, the way the outer planets orbit the sun slowly. Instead, they were racing around at nearly the same speed as stars much closer in. The only way to explain their speed was to conclude that there was far more mass in the galaxy than we could see, a great quantity of unseen matter whose gravity was holding those fast outer stars in their orbits. This discovery has its own quiet history, and it is worth telling because it shows how long it can take for the universe to force us to accept something we do not want to believe. In the 1970s, an astronomer named Vera Rubin, studying the rotation of galaxies with careful measurements, found this exact problem laid out plainly in the data, galaxy after galaxy, spinning too fast at their edges to be held together by their visible stars alone. The evidence was clear, and it was consistent, and it pointed unavoidably to the same conclusion. Most of the mass in galaxies was invisible. It took years for the field to fully accept it, because it is not a small thing to be told that everything you can see is the minority, that the universe is mostly made of something you cannot detect. But the measurements would not go away. Galaxy after galaxy told the same story, and eventually there was no honest way to avoid it. The stars we see are riding inside a much larger, much heavier structure made of something else, and Vera Rubin's careful work was one of the first clear windows onto that unwelcome truth. And it was not a little extra. It was the majority. To make the numbers work, the galaxy had to be mostly made of something invisible. This invisible matter is not arranged like the stars. The stars form a flat disk, a thin, luminous pinwheel about 100,000 light-years across and only about 1,000 light-years thick. But the dark matter forms a roughly spherical cloud, a halo that surrounds and dwarfs the visible disk, extending outward not 100,000 light-years but on the order of hundreds of thousands, possibly reaching 1,000,000 light-years or more in radius. So the true shape of the galaxy is not the flat pinwheel we imagine at all. The pinwheel is a thin, bright seed sitting at the centre of a giant, invisible, roughly spherical cloud of unknown material. When you look up at the band of the Milky Way, you are seeing the small luminous kernel of a structure that is mostly a dark sphere you cannot perceive by any means except its gravity. The galaxy you can see is a lit ornament hanging inside a galaxy you cannot. We have been trying to identify dark matter for decades, and we have failed. It is not made of ordinary atoms, or we would see it interacting with light. It appears to be some form of matter that does not emit, absorb, or reflect light at all, that passes through ordinary matter almost without notice, that reveals itself only through gravity. Physicists have proposed many candidates, exotic particles with names, and have built exquisitely sensitive detectors far underground to try to catch even a single one of them interacting with ordinary matter, and year after year the detectors have come up empty. We know dark matter is there because we can weigh it by its gravity, and it outweighs everything we can see by a factor of 5 or more. But we cannot say what it is. The largest single component of our own galaxy, the substance that makes up most of the structure we live inside, is a mystery we have not solved. And it is not for lack of trying or for lack of ideas. Physicists have proposed a whole menagerie of possible explanations. Perhaps dark matter is a new kind of particle, one that barely interacts with ordinary matter, produced in enormous numbers in the early universe and drifting through everything ever since, passing through the Earth and through your own body by the billions every second without leaving a trace. To catch even one, physicists have built detectors far underground, shielded from every other kind of radiation by kilometers of rock, waiting in silence for the faint flicker of a single dark matter particle bumping into an ordinary atom. Others have wondered whether the missing mass might be hidden in enormous numbers of dark, compact objects, faded stars or small black holes, though careful searches have ruled out most of that possibility. Year after year the detectors wait, and year after year nothing clear arrives. The particle, if it is a particle, has not shown itself. We are in the strange position of knowing, with great confidence, that most of our galaxy is made of a certain amount of something, and having absolutely no confirmed idea what that something is. It surrounds us right now. It is passing through the room you're sitting in, and it has never once in any laboratory on Earth been definitively caught. Sit with the vertigo of that. Almost everything holding the galaxy together, almost everything that gives it its shape and its motion and its gravity, is something no human being has ever seen or identified. We have mapped the stars, imaged the black hole, dated the outbursts, counted the supernovae, and all of that concerns the thin luminous minority. The great invisible majority, the dark halo that actually dominates the galaxy, remains unknown. We are living inside a structure whose main ingredient we cannot name. It is as if you spent your whole life in a house, knew every room, every door, every window, and then learned that 90% of the house was made of a material you had never seen, could not touch, and could not identify, and that the rooms you knew were only a small lit wing of a mansion that extended invisibly in every direction, far beyond anything you had ever explored. And the galaxy does not merely hold on to things with this enormous invisible gravity, it also throws things away. Remember the centre, and the way Sagittarius A star flings the S stars around at a fraction of light speed. Sometimes those encounters do more than fling a star into a fast orbit. Sometimes a pair of stars, a binary, wanders too close to the black hole, and the encounter tears the pair apart, capturing one star into a tight orbit around the black hole and hurling the other outward at an extraordinary speed. Astronomers call the result a hypervelocity star, and they have found them, real stars racing outward through the galaxy fast enough to escape it entirely. One of them, discovered in 2019 and named S5 Hypervelocity 1, is leaving the galaxy at about 1,755 kilometers every second, and its path traces back to an ejection from the galactic center about 5 million years ago. A star, an entire sun, thrown out of the galaxy by the black hole at the center, moving fast enough that it will never come back. Think about what that means for the pattern we have been tracing all night. We said, at the edge of the sun's reach, that to travel out is to stop being protected. We meant it as a description of leaving home, of drifting past the sun's grip into the exposed dark. But here, at the invisible edge of the galaxy, the phrase takes on a harder meaning. The galaxy does not just fail to protect the things at its edges, it actively expels them. It reaches into its own crowded center, seizes a star and flings it out into intergalactic space forever. To travel out in the end can mean to be thrown out, cast away from the structure that made you, sent alone into the dark between galaxies at a speed that guarantees you will never return. The galaxy is not only a machine that makes and unmakes worlds, it is a machine that occasionally discards its own stars, launching them into an exile so complete that even the galaxy itself falls away behind them. So the galaxy you can see is the small part. The real galaxy is mostly an invisible sphere of unknown matter, hundreds of thousands of light years across, that we can weigh but cannot identify. And within that invisible structure, the visible stars are a thin, bright disk, and even those visible stars are sometimes seized and thrown out entirely. The more of the galaxy we uncover, the less of it turns out to be the familiar luminous thing we thought we lived in. We have reached the point where the galaxy stops being a place made of stars and becomes something else, something mostly unseen, mostly unknown, and capable of casting its own contents into the void. And there is one more layer to reveal, one final truth about what this structure is, and it is the one that ties the whole journey together. Because the galaxy is not only mostly invisible, it is also not finished. It is still being built, and it is being built out of the bodies of other galaxies it has already destroyed. The Milky Way did not form all at once, whole and finished, the way it appears tonight. It grew, and the way it grew was by eating. Over billions of years, the galaxy has pulled in smaller galaxies that wandered too close, torn them apart with its gravity, and absorbed their stars into itself. The tidy pinwheel we picture is not a single object that condensed on its own. It is an accumulation, a thing assembled out of the wreckage of other smaller things, and we can read the record of those meals in the motions of the stars, because a swallowed galaxy leaves its stars moving in a distinctive way, a fingerprint that survives long after the galaxy itself is gone. One of the largest of these meals happened early, about 8 to 10 billion years ago, when the young Milky Way collided with and consumed a substantial galaxy. Astronomers found its remains hiding in plain sight, once they had precise measurements of how millions of nearby stars move. A whole population of stars turned out to be travelling on unusual elongated orbits, all sharing the same distinctive motion, and the only sensible explanation was that they had once belonged to a separate galaxy that the Milky Way had swallowed long ago. That devoured galaxy has been given a name, drawn from the shape its stars trace out in the data, and from a figure of the underworld, and its stars are still here, woven through the inner part of our galaxy, an entire galaxy's worth of suns that our own galaxy consumed before the sun was even born. When you look at certain stars in the sky, you may be looking at the survivors of a galaxy that died to build ours. The reason we can read these ancient meals at all is one of the great recent achievements of astronomy. A space observatory spent years measuring the precise positions, distances, and motions of more than 1 billion stars in our galaxy, building the most detailed map of the Milky Way ever made. And once you know how 1 billion stars are actually moving, the fossils of old collisions leap out of the data. Stars that were born together in a devoured galaxy still move together, sharing a common velocity and a common path, long after their original galaxy has been shredded and scattered. They are like a dye dropped into water, spread thin but still detectable if you measure carefully enough. By tracing these shared motions, astronomers have identified not just one but several separate populations of stars that came from swallowed galaxies, each one the ghost of a smaller companion that the Milky Way pulled in and consumed across the ages. Our galaxy's history of cannibalism is not a guess. It is written in the coordinated motion of millions of stars, and we have finally built instruments precise enough to read it. The streams of stars wrapping around our galaxy today are the same process caught in the act. When a small galaxy or a star cluster falls into the Milky Way, the near side feels slightly stronger gravity than the far side, and that difference stretches the intruder out, pulling it into a long, thin ribbon of stars that drapes across the sky, following the orbit of the thing being destroyed. Dozens of these streams have been found, faint arcs of stars threading through the halo, each one the unraveled remains of something the galaxy is digesting. If you could see them all at once, the space around the Milky Way would look tangled with these ribbons, the leftover threads of every smaller structure our galaxy has torn apart. It is a quiet kind of violence, spread over hundreds of millions of years, too slow to watch but unmistakable in the record, and it is still going on all around us right now. And the eating has not stopped. Right now, in the present day, the Milky Way is in the process of tearing apart at least one smaller galaxy, the Sagittarius dwarf, which strayed too close and is being pulled into long streams of stars that wrap around our galaxy like the unravelling threads of something being slowly torn apart. The two Magellanic Clouds, the largest of the Milky Way's companion galaxies, visible from the southern hemisphere of Earth, are bound to us and being distorted by our gravity, trailing a great stream of gas behind them, the same stream that Sagittarius A star lit up when it flared 3.5 million years ago. In total, the Milky Way is surrounded by more than 50 smaller companion galaxies and by dozens of streams of stars, each stream the smeared-out remains of a smaller galaxy in the process of being consumed. Our galaxy is ringed by the evidence of its own appetite, past and ongoing. The eating has left marks on the galaxy's own body. The disk of the Milky Way, which we usually picture as a flat, orderly plane, is not flat. It is warped, bent up on one side and down on the other, like the brim of a hat, and it ripples, with waves travelling through it. These distortions are most likely the scars of past encounters, the galaxy still ringing from collisions with the smaller galaxies it has pulled in and torn apart. And the Sun itself does not ride serenely in a perfect plane. As it orbits the centre, it also bobs up and down through the galactic disk, rising above the crowded plane and sinking back through it, on a cycle that takes something like 30 to 70 million years. Each time the Sun passes through the dense midplane of the galaxy, it moves through thicker gas and closer to more stars, and some scientists have wondered whether these repeated crossings might disturb the distant Oort cloud and send waves of comets inward. This is where I want to be careful, because here the science shades into speculation, and I promised you I would always tell you which is which. There is a real, published idea that the Sun's regular bobbing through the galactic plane, every few tens of millions of years, might act as a kind of clock for disturbances to the Oort cloud, and therefore for comet impacts and even mass extinctions on Earth. Some researchers have gone further and speculated that a thin layer of dark matter, concentrated in the plane of the galaxy, could amplify the effect. It is a genuine hypothesis, and it is worth knowing about. But the evidence for a strict regular cycle of extinctions tied to the galactic orbit is statistically weak, and the mechanism is unproven. There is a related, older idea, the notion of an undiscovered companion star to the Sun that periodically triggers comet showers, and that idea has been effectively ruled out by infrared surveys that scanned the whole sky and found no such companion. So the galaxy's slow rhythms may leave traces in the history of life on Earth, but the clean, ticking clock of doom that some have imagined is not something the data supports. The truth is subtler. The galaxy disturbs us slowly, statistically, over enormous spans of time, not on a schedule. There is one more meal still to come, and it is the largest of all, and it points at us from the far side of the outward view. The Milky Way is not alone. Its nearest large neighbour is the Andromeda Galaxy, a spiral even larger than our own, about 2.5 million light-years away, and it is approaching. For years, the textbook stated it plainly. In about 4.5 billion years, the Milky Way and Andromeda will collide and merge into a single larger galaxy. It was presented as a certainty, a scheduled event in the far future, the ultimate meal in which our galaxy and its great neighbour would consume each other and become something new. But in 2025, a careful new analysis re-examined that certainty and found it was not so certain after all. When the effects of the other nearby galaxies, especially the Large Magellanic Cloud, were included, the odds of a collision within the next 10 billion years came out to only about 50%, a coin flip. The one great future event we thought we could predict about our galaxy turns out to be genuinely uncertain, and if the collision does happen, it would be strange in a way that surprises most people. When two galaxies merge, the stars almost never actually hit each other. Stars are so tiny compared to the distances between them that even when two entire galaxies pass through one another, individual suns simply slide past, missing by enormous margins. If Earth's descendants, or whatever the Sun still holds on to, were present during such a merger, there would be no crashing of worlds, no rain of colliding stars. Instead, over hundreds of millions of years, the two great pinwheels would slide through and around each other, their gravity tearing both into long streamers of stars, flinging some suns far out into the dark and pulling others into new orbits, until eventually the two settled together into a single, larger, more shapeless galaxy. The night sky, over unimaginably long spans, would slowly transform, Andromeda swelling from a faint smudge into a second luminous band filling half the heavens, before the two structures merged into one. It would be the most dramatic change our galaxy could undergo, and it would happen so slowly that no single generation would ever see it move. And that uncertainty is, in its own way, the final and most fitting note of this part of our journey. We have travelled outward to the larger scale, to the galaxy as a whole and its place among its neighbours, and even here, at the grandest level, we find that the galaxy is not a finished, predictable object. It is still growing, still eating, still ringing from old collisions, still uncertain about its own future. It was built out of the corpses of smaller galaxies. It is tearing apart more of them right now. It carries the scars of past meals in its warped and rippling disk, and its own ultimate fate, the collision with Andromeda that we thought we understood, has slipped back into doubt. The galaxy is not a place we happen to live in. It is a work in progress, assembled from destruction, and it does not yet know how it ends. We have reached the far edge of everything we can travel to, and now there is only one thing left to do, which is to turn around and look back at the whole road we have walked and finally answer the question we started with. Why does our galaxy get scarier the further you travel? We are ready at last to say it plainly. So let us answer the question, now that we have earned the answer. Why does our galaxy get scarier the further you travel? The answer is this. The galaxy does not get scarier because the distant parts are unusually dangerous. It gets scarier because the near part, the part we live in, is unusually safe, and everywhere you go you're leaving that rare safety behind. We did not travel toward danger tonight. We travelled away from an accident of protection, and every step revealed a little more of what the galaxy is actually like when the protection is gone. The fear did not come from the destinations. It came from the steady removal of the shelter we never knew we had. Look back at the whole road. We began under a calm sky and learned that the calm was a bubble blown clear by exploding stars, a cavity we were only passing through. We travelled to the edge of the sun's reach and found it more than a light year away, exposed to the tide of the galaxy and the pull of passing stars. We crossed into the dark between the stars and found it irradiated and cold and full of frozen, sunless worlds we cannot see. We entered the spiral arms and found that the places where the galaxy makes its stars are the places where it destroys worlds. We measured the middle distances and found that supernovae have already exploded within a few hundred light years of us, and that only a thin band of the galaxy is calm enough for life at all. We pushed into the crowded inner galaxy and found that stability becomes impossible where the stars are packed close. We stood at the centre and watched stars flung around a point of pure absence at a fraction of light speed, above a black hole that roared 3.5 million years ago. We weighed the galaxy and found that most of it is invisible and unknown, and that it throws its own stars out into the void. And we reached the larger scale and found a galaxy still eating other galaxies, still uncertain of its own end. Every one of those layers was a protection removed. The quiet lane we live in is sheltered by emptiness, by distance, by a fortunate orbit that keeps step with the arms, by a location in the calm habitable band, by the sheer separation of the stars around us, and by the accident of timing that has kept anything from reaching in for a very long time. None of those protections is a wall. Every one of them is a coincidence, a matter of where we happen to be and when, and the further you travel from our specific address, the more of those coincidences fall away, until you are standing in the crowded, radiation-soaked, black hole-anchored, mostly invisible machine that is the galaxy's ordinary condition. The scary galaxy is not a distant, exotic place. The scary galaxy is the normal galaxy. It is our quiet lane that is the exception, and we have spent our whole history mistaking the exception for the rule. And notice that this reframing does not make our situation more dangerous than it was when the night began. Nothing about the galaxy changed while we travelled through it. The supernovae were always there, the crowded centre was always turning, The dark matter was always surrounding us, the galaxy was always eating its neighbours. All that changed is what you know. You began the night believing you lived in a peaceful place, and you end it knowing you live in a rare, sheltered pocket of a violent one, and the only thing that moved between those two states was your understanding. That is worth sitting with, because it is the real nature of every fear we met tonight. The danger was never a threat scheduled to arrive. It was the permanent condition of the galaxy, always present, always ordinary, and the only reason it feels like fear at all is that we so rarely look far enough out to see it. To understand where you live is not to become less safe. It is only to stop being fooled by the quiet. That was the illusion we started with, standing under the peaceful band of light. We looked up and saw stillness, and we assumed the stillness was the truth of the thing. But the stillness was only the view from the one calm room in a house that is, nearly everywhere else, in motion and on fire and falling and being rebuilt. The band of light overhead is a rotating machine of a few 100 billion stars and 1 trillion suns worth of invisible matter, turning around a black hole, blowing bubbles with dead stars, tearing apart its neighbours, and flinging its own children into the dark. It only looks peaceful because we are looking at it from inside the safest, quietest, most sheltered lane it contains, on a good night, during a calm stretch of a journey that lasts hundreds of millions of years. The quiet lane is real, but it is narrow, and it is temporary, and it is precious precisely because it is so rare. And here, at the end, is the counterweight, the thing that keeps this from being a story of dread. In all of that violence, in all of that crowding and radiation and invisible mass and cannibalism, one thin lane of the galaxy did something the rest of it, as far as we know, never managed. It stayed calm long enough. It stayed sheltered long enough, and stable long enough, and undisturbed long enough, for something to slowly assemble itself out of the wreckage of old stars. Atoms forged in the spiral arms gathered into a world, and on that world, over billions of quiet years that the crowded galaxy could never have allowed, those atoms arranged themselves into living things, and those living things eventually became complex enough to look up and to wonder and to measure. Every fact I have told you tonight, the distance to the centre, the mass of the black hole, the speed of the S-stars, the invisible weight of the halo, the corpses of eaten galaxies, all of it was worked out by creatures made of galactic debris, standing on a small planet in the quiet lane, turning their instruments on the thing that made them. That is the strangest and most beautiful fact of all. The galaxy is mostly invisible, mostly violent, mostly hostile to the long stillness that life requires, and yet one small part of it, one fortunate lane, grew something that could map the whole. We are the part of the galaxy that looked back at itself. We are the place where this rotating machine of stars and dark matter and black holes became, somehow, aware of its own shape, its own danger, its own history. The galaxy spent billions of years being scary in the dark, unwatched and unmeasured, and then, in one quiet corner, it opened an eye and began to understand what it was. That eye is us. That is not a small thing. In a structure this large and this indifferent, the appearance of something that could comprehend it is the rarest event of all, rarer than any supernova, rarer than any collision, and we are it. So go back outside, on the next clear night, and look up at that soft band of light. You know now what it is. You know it is a bubble blown by dead stars, an arm that makes and unmakes worlds, a crowd too dense for stability, a centre that roars, a halo you cannot see, a machine still building itself from the bodies of other galaxies. You know that the further you travel into it, the scarier it gets, and you know exactly why, because you are standing in the one quiet lane, looking out at the rest. But you also know that you are the part of it that looked, and there is a kind of peace in that, a deeper peace than the false calm we started with, because it is a peace that has looked at the whole terrifying structure with open eyes, and found, in the middle of all that violence, the one small sheltered place where something learned to understand it. That place is your home. It is narrow and it is temporary, and it is the safest and most remarkable address in the galaxy. Rest here tonight. You are in the quiet lane, and the quiet lane is holding, and above you the whole enormous machine turns on slowly, and for now, gently, around the small warm world where the galaxy first learned to see.